to support compositional programming for these effectful isomorphisms. Like if we have a pair of functions converting between x and y, we can use the first combinator to make another synchronization between pairs so that the functions are used to transform the first component of the pair. And similarly, we can also have combinators for sums. So the two pairs of transformations are used respectively to transform the left and right branch of a sum. So the problem is to characterize the interaction between two effectful computations and to establish some nice structure about this interaction. And it should also support combinators such as product and sum, as we have just shown. So if we just use the Kleisli composition, we can start reasoning with monad laws, right? So for example, for the first combinator, we consider first F followed by first G. Then we can first expand the definition of first F and use monad laws, specifically here associativity, to rearrange things. And then we eliminate the pure by using identity, and then expand again, and then rearrange. So we see that first F followed by first G is inverse to each other if and only if F followed by G is inverse to each other. But the problem here is that when we use different monads in the two directions, now all of a sudden we cannot compose F and G together because we no longer have the Kleisli composition. They are different monads. And it is well known that composition of two different monads may not still be a monad. So in our ICFP paper, we used an approach by working without the composition. We use a relation called the round-trip relations. So this relation is a generalization over pure function inversion. So for pure functions, we say that G after F is ID, is saying that G and F are inverse to each other. Then for effectful computations, we say RFG is the relation for first run F and then run G, and we must get back the original input. So it's a direct generalization of the inversion relation. And for this relation to make, for it to actually describe something that's meaningful, we need a set of laws or axioms for this relation. So we had identity, composition, and these two for the category structure. And we also have product and sum to support the product and sum combinators. And finally, we have this very exotic looking, but still necessary axiom, which specifies a very specific situation. So if we look into this axiom, we see that two pure computations, F and G, are happening in between the composition, right? So we have lift F and lift G happening in the middle of the composition. So really, if we can compose the two Kleisli arrows together, so if they are using the same monad, then sure, these two are equivalent, right? Because they compose to the same thing. But because we don't have the composition structure, we have to use an axiom to specify that this is true. So by checking all the axioms, we see they're really calling for a real composition structure between the two Kleisli arrows using the two different monads. So let us be clear that these axioms actually serve their purposes well. So they really support a rich combinatorial language, and they are shown to be satisfied by all the common effect combinations. But there's one problem, is that we are really doing the composition. We're composing two arrows without saying that it is a composition. So what we want is a real composition structure, which will make most of these axioms redundant, okay? So let's introduce the free composition. So while working towards a composition structure, we consider this bind operator, which is missing because M and N are different monads. So we don't have appropriate monadic bind operator for this, but we can try to do as much as possible to combine the two. So recall that for a monad, a bind is just a functor mapping followed by a join, right? So the join is the monadal structure in the endofunctor category. So for this specific setup with M and N to different monads, there's no join, but we can still map. So we have this bind operator decorated with daggers, for lack of a better notation. We cannot join, but we can still map. So we just use fmap to combine the two things. And if you are familiar with the Yoneda lemma, you can see that this is an instance of the co-Yoneda lemma, right? And here we introduce this new symbol O times, which is exactly the same as the regular functor composition. So f O times G is just f composed with G. But we use this symbol to highlight the boundary between the two functors. So on the left-hand side of this operator, it's the effect for the forward direction. And on the right-hand side of this operator, it's the effect for the backward direction. So we make this clear by using a different symbol. And if we consider a chain of effectful computations, we see that we can combine M and N into the composition M composed with N. And we can also extend this composition on the left with M and on the right with N with these trivial definitions. So it might be even more intuitive if we consider the composition in terms of join instead of bind. So if we think of all these compositions in terms of join, we see that the first composition is just an identity. It's lifting from M composed with N to M composed with N. So it's an identity. And for the other two, it's really just absorbing the extra M or N into the composition structure by using the respective join for the respective monad. But the problem here is that it's not really a monad. It only allows certain compositions. So for example, we cannot extend on the left with an N or extend on the right with an M. So it's not strictly a monad, but still is some structure. And as it turns out, it's actually a polymonad. So for most of you, I guess you won't be very familiar with polymonads, so I'll give you a quick definition. A polymonad is just a generalization of monads. So first, we have a collection of functors. One of them should be the identity functor. And we also have a collection of bind operators. It is, or equivalently, the join operators. It combines M with N, and it gives rise to a P. And it only works for certain triples of M and P. And by using this bind, we can derive the fmap operators and the monad morphisms, those lifts. And polymonads also have laws, which are generalization of monad laws. And among them, there's the associativity law. So it turns out that the composition we just defined actually forms a free polymonad. The monad has this collection of functors, the identity, the two monads M and N, and the composition M composed with N. So by being free, it means for every polymonad with the composition which can compose M and N into a P, we have a unique lifting from our composition to their composition P. And this lifting is just by binding with ID. Just like for usual monads, you can define join in terms of bind with ID. And the property for this lifting is that it preserves the polymonad compositions. So it preserves all the composition structures. And this result follows from the associativity law for polymonads. So what's the significance of this structure being free? It means we have maximum generality. So as long as there's a property can be formalized on some notion of composition, as long as can be formalized using a polymonad, it can also be formalized based on this free composition. So it means we have full generality. So let's see how we can reason about these effectful computations using this free composition. first, we had the identity and composition laws for the round-trip relations. Now we can also have the identity and sandwich law for this free composition. So this P predicate accepts two things, a value X and a monadic action M, or actually it's not a monad. It combines the two monads M and N. And it basically says this action M behaves like X. So it returns X, and it does some effects, but it doesn't disturb all the other effects. So it behaves like pure. And the identity just says that pure, if the two directions are both pure, then sure, it satisfies P. And sandwich law says that we can extend an arrow F on the left and on the right with two other computations with the respective types. So that's all very natural. And what's good about this new formalization is that all the other axioms become theorems. So we can actually prove them. For the product, as we just saw, using the first combinator, we can start with this composition and do basically the same as in the monadic situation. We just expand the definition and use the associativity law and identity law, and then expand again, and then use associativity with identity to have this sandwich structure, which fits directly into the previous sandwich axiom, where we can apply that axiom and simplify everything so that the composition of first F and first G follows from the composition of F with G. And we have a very similar situation for sums. So we can still start with its composition and expand by definition, reassociate, eliminate identity, and expand again, and form this sandwich structure where we can apply the other axioms and get the theorem we want. So these are how we can reason about the composition of two effectful computations using this new free composition we just defined. And now we can see some examples for how we can specify useful properties over the composition between different effects. So we start with something simple. We consider the array effect. So from this definition, we can see that the forward direction uses the effect array E, and the backward direction uses array E prime. So they are different effects. And so the forward direction can report the array E, and the backward direction can report the array E prime. We can have a strong specification over the interaction between the two directions by saying that if the forward direction fails, then everything is fine. Or if the forward direction succeeds, then the backward direction must also succeed, right? So that's an interaction between two formal computations. And we can also weaken the conditions by saying that even if the forward direction succeeds, we can still have the backward direction fail. So this relation then says that only if the two directions both succeed, then we have the original input value recovered. Then after that, we can also consider some other common effects like the reader for a shared context, right? So usually we can consider this reader in terms of the reader monad transformer, this reader T. And here we can define the predicate by lifting the base property P0 to the property P on the reader effect. So suppose we have some specification over the interaction between the monads M and N, then we can lift this specification to the interactions between reader T as M and reader T as N. So this lifting can be just directly defined by interpreting the two reader T effects and supplying them with the same context S. So this lifting really says that the two directions share the same context S. And all the other things are delegated to the base property P0. And similar to reader T, we can also define something for the state T transformer we still leave some base property P0 to P. And the interpretation just says that if we thread the same state through the two directions, the state must also be recovered. So we are treating the state as part of the input and the output in the base property P0. Right, okay. So that's all the examples I have for today. And we can conclude by saying that different monads can still be composed for free, but we do not get another monad from the composition. Instead, the composition forms a free polymonad structure. And the composition is performed in sequence. So it means first we perform the effects from the first monad M, and then we perform the effects from the second monad N. And we can reason about this composition just like normal monads, using all the familiar properties like identity, associativity, and all the other laws we are familiar with. And finally, we can use this free composition to describe the interaction between the two directions of a bidirectional program. And if you are interested in more details about this part, you can welcome to the presentation tomorrow at ICFP. And yeah, so I guess that's it. And thank you for listening.
Question?
Yeah.
So like one about the more general use cases, like would we be applying like rules and say more verification or root cause subprograms?
Okay, so I guess the question is how this can be used in formal verification.
Yeah.
Okay, so it's actually a development of our work on effectful lenses, which is a specific type of bidirectional program. So we add effects to lenses, and we are actually using the round-trip relation to prove properties for those effectful lenses. So the intention of this development is that we can replace that reasoning with this free composition. So we can rebase all the theorems and all the theories, all the combinators, all the reasoning in our ICFP paper with this thing. So everything can be simplified and we get fewer axioms. So before that, we have 5 axioms, but now we have only 2 axioms for identity and composition. And all of the others can follow from that. So yes, indeed, it's for formal reasoning. Yes.
Okay, listeners. Okay, so I have one small question.
Yeah.
Maybe I'm wondering you could use this resistance for the equational reasoning, but you have some applications of the composed reason about the
So I'm not sure if I understand the questions, but yes, indeed, all these reasonings are using equational reasonings, right? So
maybe it's the general.
oh, right. Okay. Okay. So
some specific example in where the issue. One of some conditional rules other combines to get answer. So the one specific equational
yeah. Okay. So I guess the thing is we want to separate the concerns, right? So we can have a generic combinator framework based on the general theory. So without knowing the concrete monads, we can still reason about them. That's for the abstract reasoning, which I have shown here. So we don't know the 2 monads M and N, but we can still do this reasoning and say that the first combinator and the sum combinator can be used for arbitrary effectful bidirectional programs and it will still work, and it should preserve all the properties. But yes, in terms of more specific effects, we can have some more specialized treatment. Definitely for specific effects, you will need specific combinators, such as, like, we had a local combinator for the reader effect in our effectful lens framework. And you can imagine to have something similar to like a modified combinator for state and all the others that you can imagine. And actually, I had some backup slides for some other specific effects, like non-determinism, right? We can have different specifications for the interactions between two non-deterministic computations. And as long as these specifications satisfy the two axioms we require, then all the other things follow. And we can apply the whole theory to this specific situation.
Okay, yeah. Okay, so, yeah, let's something.